Hello again. This is Math 2232 coming to you from the College YouTube page, and the title of this lecture is Volumes for Solids of Revolution, Disk and Washer, also known as the ring technique. As always, please be an active learner as you watch these videos. By way of introduction, in this section we start look at solids of revolution. And so what we will have is a function in the plane, and we will be spinning it around an axis, and in this case we're spinning it around the x-axis. That's what this notation means. Now when you do that, you create a solid, and in particular if you look at this is a solid line, you create a solid that looks like this. And so we want to know the volume of this solid. So we rotate this curve about a given axis to get a surface of the solid of revolution. For purposes of this discussion, let's rotate about the x-axis, although it could be any vertical or horizontal axis. We'll say more about that later. Doing this for the curve above, over here actually, gives the following three-dimensional figure, and we want to find the volume of this object. So here again is a picture of what the area is that we're rotating around. And what we're going to do is we're going to follow our program that we normally have had of slicing this into pieces. And so we're going to be picking delta x, slicing into pieces, and we're going to slice the interval from A to B into n pieces, and those are going to be in equal pieces, and those are going to be called delta x. And then we're going to pick a point within each of those sub-intervals to find the area. So you see, when we've done that, we will have these intervals, which will be the heights of these cylinders, and then we will have the cross-sectional area for that point, and the cross-sectional area for that point will be the area of, in this case, a circle, because of the way we're spinning it around the axis, a circle of radius, in this case f of x. So anyway, the volume of this region then, this region can be approximated by the finite sum. V is approximately equal to the summation of these cross-section areas times delta x. And the exact volume would be the limit as n goes to infinity of these, which is going to be the integral of a of x dx from a to b. So in the case, the volume will be the integral of the cross-section area at any x a of x. Note that in this case the cross-sectional area is a circle, and we could go further and get a formula for that, and we're going to do that in a bit. However, the formula is much more general, and also we could do slices along the y-axis and do the integration along there, so the volume would be either this expression which we derived or this expression which would be going along the y-axis. Okay, now one of the easier methods for getting the cross-sectional area is to cut the object perpendicular to the axis of rotation. Now this is characteristic of the disk, washer, or ring technique. So if you're doing the disk, washer, or ring technique, you're drawing a slice that is perpendicular to the axis of rotation. And when you do this, you'll either get a solid disk, if the object is solid, as our first example is, or a ring if we hollowed out a portion of the solid, and we'll see this eventually. Now, the area of a circle is going to be then, the solid disk, the area, cross-sectional area is going to be pi times r squared, and the radius will depend on the function and the axis of rotation. Now in the case we have a ring, where we have an outer radius and an inner radius, the area is going to be pi times the outer radius squared minus the inner radius squared. So you want to remember this, you want to remember this, and you want to remember that this is called the method of disks or rings. Let's do this example. Determine the volume of a solid obtained by rotating the region bounded by y equal x squared minus 4x plus 5, x equal 1, x equal 4, and the x-axis about the x-axis. You know what to do. Let's see how you did. Well, the first thing to do is to draw the picture, and pretty quickly you realize that this is the example that we've been working with. Here is the area that we're revolving around the x-axis, and we'll get something that looks like this. Now, if you look at this cross-section area, or any cross-sectional area, you see that you're getting a circle. So the volume is going to be there's the circle, and the radius is going to be x squared minus 4x plus 5. And so what you're going to be doing is you're going to be squaring that, because the area is pi r squared. And so that is going to be pi times. Now when you square a trinomial, you get kind of a complex thing. There's quite a bit of algebra involved, but you should be able to do this algebra, and I encourage you to do it. And then you need to determine the limits of integration. Now in this picture it's pretty clear that with x you're going from there. And notice that we were slicing perpendicular to the axis of rotation. That tells us that what we're doing is a disk method, but that also tells us that we're integrating dx. So a as a function of x is this, which we simplify to this. So we integrate from 1 to 4 this. We add 1 to the exponents and divide by the new exponents through all of these. Plug in the numbers and we get 78 pi over 5. Now that's the exact answer. That's what I would expect you to come up with if I ask you a problem like this on the test. The first part is to always draw the circle, draw the slice, and set up the integral. Here's another problem for you to consider. Determine the volume of the solid obtained by rotating the portion of the region bounded by y equal, this is the cube root of x, and y equal x over 4 that lies in the first quadrant, and we're rotating this about the y-axis. You know what to do. Let's see how you did. Picture should look like this, and you're going around this axis, so you're holding this square and you're rotating around that, so it gets something that looks like this. So we're taking and we're getting these are the volumes that we're getting as three-dimensional things as they go around. Okay, now I didn't tell you what we have here, but if we're again doing the disk method, we're going to be drawing slices perpendicular to the axis of revolution. And you see in this case we are getting a ring, not a disk. And the outer radius is going to be this line, and the inner radius is going to be formed by this line. And also, you know, because we're drawing the slices this way, we're integrating dy. So that means we have to write these things as functions of y. So y equal the cube root of x is going to be x equal y cubed. And y equal x over 4 is going to be x is equal to 4y. And so the area in this case is going to be a of y. And here you can see that the 4y is the outside radius, and the y cubed is the inner radius, and this is the is what we're calculating. So the area is going to be pi. This is going to be the outer radius whole squared minus the inner radius whole squared. And when we simplify that, we get pi times, this is 16y squared minus, and this is going to be, since that was y cubed, that is y to the 6th. And we're going to be going from 0 to 2, because that's where the y's go from for this. You could also find that by finding the intersection of these two curves, setting them equal. Okay, so we go from, it's pi, the integral from 0 to 2, 16y squared minus 5y to the 6th dy. We do the integration. Make sure you follow this calculation and you get the exact answer, which is what I'm always going to be looking for, is 512 times pi over 21. Here's another example for you to consider. Determine the volume of the solid obtained by rotating the region bounded by y equal x squared minus 2x and y equal x about the line y equal 4. You know what to do. Let's see how you did. Okay, this is the line that we're going around, and so notice that this is where you put the little arrow, and things are going to be different. This is going to be a ring upon analysis, and the outer radius is going to be going from this blue line, blue curve rather, up to that line, and that distance is going to be the inner radius is going to be, and again, this time we're slicing it this way, so that means we're integrating with respect to x, and so it's going to be this curve minus 4. And the inner radius is going to be 4 minus, and this has to be in functions of x. So the inner radius is going to be 4 minus x, and the outer radius is going to be 4 minus the whole of that blue function. And so we get this. So the cross-sectional area is going to be pi times the outer radius minus the inner radius, both of them being squared. So it's pi, the outer radius squared, minus the inner radius squared. We simplify that. There's actually quite a bit of algebra sometimes involved in these problems, and you will be doing this algebra. So the volume is going to be the integration of that. We add 1 to the exponent and divide by the new exponent, and we plug in the numbers, and we get the final answer is 153 pi over 5. Doing these problems as practice would be great preparation for an assessment. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.